Welcome everyone. In this video I'm going to talk about a very simple displacement sensor. I took a picture of the setup and I put it in an image editor software, so it will be more easy to draw and write some things which are important. So that's what you can see on the screen. So let's jump into the parts. So the main part of this is of course here. This is an Arduino Nano. Basically I'm just using it for the I2C bus and to use the 5 volt output of it. So first let's talk about the 5 volt the usage of the 5 volt output. So you can see it that it goes here. So we have the plus 5 volt goes into this part, which is a DC-DC converter basically, or a voltage regulator. Let me write it down. This is basically a ADS1115 chip, just right here. And here you can see a trimmer potmeter. I just write like this. So you can change the output voltage as the function of the resistance basically. So you have some input voltage between some values. I think the maximum that you can apply is around 40 volts, but I'm not sure. You should check the datasheet for this kind of circuit. But what I do with this kind of thing, that I'm using the 5 volt output of the Arduino, which is in principle it's roughly 4.8 volts under the load of all of these instruments. So I'm using the 5 volt output, and then I bring it down to roughly 2.05 volts. So I measured this with a multimeter, and then this 2.05 volts goes down to this linear potmeter. So this is basically the linear sliding or slide potentiometer. So what it does, that we have basically this range of motion, which is 60 millimeter. So as you go up and down with this slider, then you can change the voltage on the output basically. So this is a regular potentiometer. You can find it in mostly in audio stuff, and you have to be careful. This particular piece is actually logarithmic. I found out during I was working with this, so it doesn't have very nice curve. And of course in the beginning, when you start to change the position, then the voltage will change just a little bit, and then in the middle part there will be a sort of linear part of the curve, and at the end you have another slowly changing region. So, but let's say that this is a linear potentiometer, then it means that as you go with the distance, just call it D, and then the output voltage, and that should be something linear. So as you go, this is now the 0 position, and let's call this the maximum position regarding the physical dimension, the length of this section, and also the voltage. So now we are at 0 volts, and then if we go down, we get the maximum input voltage, which comes here on the output. So how we can use this? So basically I want to use this as a displacement sensor. So there will be some device which will move this slider, and by measuring the output voltage, I can calibrate this voltage as the function of the distance. So I'm just using some caliper or some ruler or whatever, and then I can check at certain distances that, okay, now at 0 I'm reading 0 volts, of course, and then halfway, so at 30 millimeters, I should read roughly the half of this input voltage, and then at 60 millimeters I should read the maximum input voltage, more or less. So that should be the principle of this, and by that I can get the function and just simply calculate the distance based on the random voltage which I can get from the random position of this slider. Or I can say that I totally trust this kind of setup, and then I know that I have some certain range for the AD converter, analog digital converter, and I just assign the lowest bit to the 0 position and the highest bit to the maximum position, and then I just say, okay, if the bit is halfway between the 0 and maximum values, of course the slider should be halfway as well, and so on and so on. So now I mentioned the AD converter, so this guy here in the middle. So this is, I don't know if you can read it, but this is a ADS1115 16 bits and I2C connection. So basically we just use two cables for the data, or one cable for the data, one for the clock, and then two cables for the power supply, plus minus. And then we have basically 4 inputs. Inputs, there should be an N. So you can see from A0 to A3, and these are the single-ended inputs if you use 4. So basically you use one of the inputs as a plus or positive, and then you use the ground as a negative, and then you can use the range of this. And if you use it as a differential, then you only able to use 2 channels, because you have to pair up these channels. So basically one channel will be A0 as the positive, and A1 as the negative side, and for the channel 2 you will have the A2 as the positive and A3 as the negative. So these are 2 channels, and this is a bit more precise. So if you have some noisy environment or noisy source, or you want to have really precise readings, then I suggest you to use the AD converter in a differential mode instead of the single-ended inputs. And also this device supports the PGA, so basically it has a built-in amplifier, gain amplifier. So basically what you can do is you can restrict the voltage range to some certain regions, and you can divide that range with the number of bits. And now I will go to the next slide, and I will tell you how I use the PGA here, and why I chose to have the input voltage here on the slider potentiometer as roughly this 2.05 volts. So we stopped at the PGA, so let's go back to this part. And then this ADS1115 has 6 PGA settings. So basically the first one is like the first one is 2/3, and then 1, 2 and 4 and 8 and 16. So what you do is that basically you change the range. So this is like the PGA, and this will be the range in volts. So this is plus minus 6.144 volts. So you measure between plus and minus 6.144, and then if you go down to 1, then you measure between plus and minus 4.096, and then so on and so on. So from this 1, 2, 4, 8 and 16, you just divide the voltage by 2. So let me complete this list. So it's like this. So you can see if you use a large gain, then you measure between basically 256 millivolts plus or minus, plus and minus. So I picked the number 2, this, and I will tell you why. So basically the input voltage for the potmeter, so I just call it pot, is somewhere around this. So it's very close to the upper region. So what we do with this AD converter is that we know that the resolution is 16 bits, which means that it is able to distinguish 65,536 different levels. So what you do in principle is that you divide the voltage provided by the PGA setting into 65,000 equal parts. So if you just combine these two things, that means that you measure between plus and minus 2 point something. So this is like, I don't know, start with minus. So 0 is here in the middle. So you have 2.048, and then you have plus 2.048. So in principle the whole range is 4.096 volts. Whatever, this is not necessary. So in principle you divide these 4 volts into 65,000 pieces. So that means that yeah, basically just divide this with this number. So we divide it by 65,536. So that will be equal to 0. I just write out the whole number here, watts. So basically this equals to, if we remove all the zeros and everything, microvolts. So in principle, if you have, let's say, a perfect potentiometer, then you can divide the steps of the potentiometer into 62.5 microvolts. So you can read the differences with this good resolution here. And this is very nice. So it's you can measure very fine displacements. and that's very useful for this, because you can make a very cheap displacement sensor with this, but you have to suppose that the potentiometer is mechanically perfect. But you should also know the following. So I showed you this, that we are measuring between, okay, now I just use it for the sake of simplicity, between plus and minus 2 volts. But we are in principle just using the positive part. So in fact we lose half of our range. So we are only using the half of the full resolution. So in principle we are just using 32,768 points out of the 65,536 points. So this is what we have between 0 and plus 2.048 watts. So our resolution could be improved if we could squeeze all the 65,000 points into this area. But now we don't care about this because we already have very good resolution, like this 62.5 microvolts, and that's just perfectly enough for this very simple demonstration. So this is what we have here, but you should keep in mind that if you want to improve your resolution, then you should think about the range. So it's very important. And coming back to the input voltage, which I generate with the voltage regulator, or which I convert from the 5 volt output of the Arduino board, is I chose the input voltage to be, let me write it down. So I chose the input voltage to be roughly the same as the upper part of the range of the PGA. So I can use the potentiometer efficiently. And of course, if I want to get more fine resolution, then I can further increase the or decrease the input voltage, and therefore I will split up the range of the potentiometer into more fine steps, but this is already enough. And why is it enough? Well, if we take the length of the potentiometer is 60 millimeters, and then within this 60 millimeters we have this 32,000 steps. So if we divide 60 millimeter into 32,768 parts, then that means that I don't know, let's call it X, that is 0.01 roughly millimeter, which is 18.3 micrometer. So in principle, if we say that everything is perfect mechanically and electronically, then the resolution of the potentiometer with this setup what we have here is 18.3 micrometers, which is very, very fine resolution, and I don't really believe it. I would say that the real resolution could be much much more worse. So maybe this can be even 10 or 100 times larger, but at least 10. But you can see that if we idealize everything, then we can detect very small displacements with this linear potentiometer. So I think this is very good, because you can have some nice projects which could use some kind of distance or displacement measurement, where you can create some mechanical contacts between the moving part and this slider potentiometer. So I think it's very useful and very powerful. And now I will demonstrate to you the very simple code, and I will show you the output of this code as well, so you will see how to read the signal. But basically this is just a AD conversion, and you just read the signals of the potentiometer. But still I show you how it works. So here we are with the code. So basically I just wrote down the pins, just so I know what is what, and we just include this we include these two libraries, wire and Adafruit ADS1115. You can search for this within the Arduino software, and you will find it, and you just simply download it. And then I just defined some random variables which I will use later on in the future. And this is basically the setup part. So I don't need very quick sampling. However, this device is capable of much quicker or much faster sampling. I am just satisfied with this 128. And then I chose the gain 2 setting, which is the already mentioned plus and minus 2.048. And then this is just to start up the AD converter. And then I just simply print some message. And in the loop I will run one of the functions. I wrote two functions. One is with the differential input and the other with the single-ended, and then I apply 1 second of delay. So in each second I will refresh the output information. And then just let's quickly go through the differential part. So I'm reading the bits first from the channel 1, let's say. So that is the A0 and A1 input. And then I immediately print it. And then I read the second channel, but I'm not using it, so it's not necessary to read it. If you have some very time critical tasks, then you can skip this. And then I write the percentage. So basically this is varies the potmeter in percentage between the 0 and the maximum point. And then I print it, and then I convert this to the voltage. I already showed you the voltage, I mean how the voltage gets calculated from the reference voltage or input voltage. So this is how you do it. You multiply the bits with the resolution basically, and I do this division to get the output in volts, and then I print it. And then you can just repeat this with the second channel. And then later on I will implement the distance with my calibrated stuff. So I will calibrate it with a caliper, and do it. And of course I will also compare it with the mathematical method. So I basically just divide the distance and the bits equally. So the 0 bit will be at the 0 point, and then the maximum bit will be at the maximum point of the potentiometer, and I just use this linear relationship. But now I have a logarithmic potentiometer, and I don't see the point to use that because it's not efficient. So maybe I will do another video where I demonstrate this again. And then I just put this here so you can read the AD converter with the single-ended inputs. So what you do, you put the positive wire on the A0 and you put the negative wire on the ground. And this is, yeah, I just go through all the steps in the same fashion as I did. So let's connect to the Arduino now. So what you can see is I print these 3 values every second, and now the potentiometer is at 0, of course. So now I will start to slide it towards the maximum. So you see it's changing. And in fact, now I moved it like 1 centimeter at least. So, but if you see the values, that is not really corresponding to the 1 centimeter in the percentage, for example. So that's not 1/6. So it's like it should be something like 17% already, but due to the logarithmic potentiometer, the initial part of the change is not really, let's say, strong. And then now I move it like halfway, then this will be roughly halfway as well. So you can see, but then if I start to increase again, I just moved a little bit from halfway and we are already at 80%. And you can see the voltage is also the same, so the mathematical formulas are fine. And now I almost saturated the potentiometer, but I still have like ½ centimeter left, so now it's like, yeah, saturated already. So now there is a small, let's call it dead spot, where I can move the potentiometer without having different reading. And I'm still within the, I should be still within the range of the PGA setting, but due to the potentiometer it's like not working linearly, of course, because it's not a linear potmeter. So this is what we get. But you can see that it's just a simple potentiometer reading, and you can do this basically in real time. So it's so fast, even with 128 samples per second, that you can refresh everything in real time. Now I just move it back and forth. And I'm printing 6 digits for the voltage, and now I haven't touched the potentiometer, and you can see that it's very, very stable, so we can trust it, I guess. And now I move it again, and you see that the variation, if it happens with the 4th digit. So that's like in the millivolts range. So that's, for me, it's negligible at this moment, because I don't need that great resolution. But you can see that it's, once the setup is stable, then you can get very, very stable readings as well. And then the bit is like jumping between 14,685 or 86 sometimes. So just plus minus 1 bit is a very good stuff. So you can see it's very stable. So I think this was all. I will finish the video here. So I hope this small demonstration and explanation was somewhat useful for you. And in the next video I'm going to create a new circuit with a linear potentiometer, and hopefully I will also build in this displacement sensor in my tensile testing machine, because my ultimate goal is to use 1 or 2 potentiometers to measure the displacement of the crossheads or grips in the tensile testing machine. Because if I can do that, then I have everything, the displacement and the force measurements as well, and then I can finally use the tensile testing machine as it should be used. So I don't know what will be my next video about, but I hope that I can release it soon and you will see a good progress with the tensile testing machine. So see you next time.